stud plates or plate slab connections, but for stud plates, the roof load, as I said earlier, the roof load still continues across, hits the top plate and down through the walls. So whatever your ULW was for your common rafter plate connection, that's what it will be right down through the wall, okay? So the ULW still remains the same. Half the distance between connection, we worked this out before, plus the overhang, which was 1286. That's the connection, that's the calculation there for it. Spacing, because our studs are 600 apart, half the distance between connection plus half the distance between connection, 0.6. So when I did the multiplication here, ULW times spacing come to 0.77 of a square metre. It's still in that second row, okay? So the pressure is 1.33 times 0.77 equals 1.03 kilonewtons in total. What I did then, I went and had a look for a connection. And I went to table 9.19. I went to table 9.19 in the book, and where I come up with the connection is down here at the bottom of the page. And I'm on page 192. 192. And what I come up with was a type D connection, which is a stud strap at the top plate and a stud strap at the bottom plate. And the total value of that type D connection is 2.9 kilonewtons. Now my question to you is, apart from our friend in North Queensland, when have you ever seen a stud strap on every single stud? And the answer is never. You've never seen it. What you would see is where the stud strap is either at 1.2, 1.8 or 2.4. Now just to prove to you what that's about, 2.9 kilonewtons there, what I did was change this to 1.2. I'm not going to put that stud strap on every stud, I'm going to put it on every second stud. So that meant the distance between connections is now 1.2. When I multiplied it by that, I come up with 1.54 square metres. So I've increased the tributary area by making a wider spacing. Then when I multiply it by this, I come up with 2.05 kilonewtons of resistance, which I can still use the same connection. It's equal to or greater than. It's a lot more efficient to put them every second stud. That's what it's about. I can even change that again and push that out to 1.8 and do it on every third stud. That means we come up with 2.31 square metres, which in turn gives me 3.07 kilonewtons of resistance. Now when you come to here, what you actually do then is move down to the next row and it changes that to 3.8. So I'm on, that's 3.8, that's 3.07, that'll still work. So at 1.8 metre centres, that's how they do it. And even then you could move it out to 2.4, so on and so forth, to get it as economical as you can. You want to have that gap, instead of the gap being that wide, you want to have the gap down about that wide, if that makes sense. You need to get the value of the connection as close as possible to the value of the resistance that's actually required to stop the thing from blowing away. So that was the purpose of me always saying to you, think about the distance between connections. Now when I do when I do a bottom plate slab connection, and I'll just tell you this, I can work it out so that I can put a fixing every 600. I can work it out so I can put a fixing every 1.2, and a fixing being a concrete nail. But when I push them further apart than that, what you actually find we looked at those figures this morning, about 8 kilonewtons for an M10 chem set. You can actually push those fixings apart to about 4.2 metres. And they will fall within what you actually require, depending on the wing classification. Now that's not practical, okay? But what you can do from a practical point of view is put a put a chem set in every 4.2 and then a nail in between it. And the reason it's practical is to keep the bottom plate straight. That's why you'd be doing that. Simple as that. That's what it's all about. So that's how you play with the numbers. And this is why I keep saying to you, think about the distance between connections. It's so important. Don't think about spacing or whatever else. It's about the distance between connections. okay? Let's close that chapter of our lives and get on to bracing. Bracing. Now, procedural flowchart. You don't actually have a chart. What you have is a written version of this. And what you've actually got written here in clause 8.31 is this up here. First thing you need to know is the wind classification. With bracing, we're not interested in whether it's a tiled roof or a sheet roof. A roof is a roof is a roof from a bracing point of view. The next thing you need to know is determine the wind pressure. And pressure before in tie down was quite easy. Pressure in bracing is actually a little bit technical. If I could quickly introduce you to one of these little lovelies, these are the pressure tables, okay? After a while you're going to end up with squinted eyes and cross eyes and everything else trying to work these pressure tables out. Then you determine the area of elevation. Once you work out what the area of elevation is, actually a good way to explain the area of elevation is quite simply, pretend you're standing here, you're facing the west as the sun's going down. What proportion of that house is blocking the sun? It's quite simply, that's what the area of elevation is. One more thing, if you look at that plan, isn't that plan called an elevation? There it is. So what is the shape? There it is there. Go and work out the area. It's just a little bit more complex than that, but not much more. So that's basically what it is. And then once you've done that, you've got to calculate the racking force. Racking force equals area times pressure. Hang on a minute, what's this? It's exactly the same. Force equals pressure times area. It's the same principle. Area is actually a fair bit simpler now. There it is, there's the dimensions, work it out. Reading the pressure is the bit that's a little bit different. Once you've done that, you then design the bracing system, and then you've got to do the distribution. And the distribution is the difficult part. Putting distribution into reality. We can do it here in heaven really easily on the board because there's no doors and windows in my design here. It's quite simple. Ply bracing on the external walls, strap bracing on the internal walls, they're the golden rules, that's it, full stop. Except when you introduce windows into it, that's when it gets a little bit difficult. And it's getting harder and harder these days where we've got these massive openings, 6 metres long with multi-folds in them and so on and so forth. You've got very, very little space to deal with to put your bracing in, so it is getting a fair bit more difficult. And then once you've done that, you've got to determine the fixings. And we're not worried about that for task 57, but that's what we're going to do. Okay, so step 2 is determine the pressure. Now I want to introduce you to these tables. Table 8.1. When you look at table 8.1 here, can I just ask you a general question? What can you see in that diagram that's consistent, in those diagrams, that's consistent with all those surfaces? Can you see anything? Exactly. He's saying the roofs aren't raked. It's a flat surface. And as a consequence of it being a flat surface, when you get down the bottom into your wind classifications, you'll see they're consistent for whatever that wind classification is. In other words, for N3, it has a resistance of 1.4 kilopascals. Because this is a flat surface, it's 1.4 kilopascals in the centre, it's 1.4 down here, it's 1.4 up here, and up here. Again, think about the spinnaker on a sailing boat. If it's parallel and it's this flat surface, it's catching all the wind that's hitting it, okay? Even though it's a curved, think about it as a flat surface. So that's what's consistent there. So what you do in that case, in order for you to use that table to get your pressure from, is you'd look at the elevations on the plan and you determine whether it is a flat surface or not. And if it's not a flat surface, you can't use that table. If it is a flat surface, that's the table you'd use. Table 8.1, as I said, was where you've got gable ends, flat walls, skillion ends, and it varies with the wind classification. Now what I want you to do, go to table 8.2 there. You see all this written across the top. Let me just read you one of them, this one. Pressure on area of elevation, single or upper story of 2 stories, long length of building, hip or gable ends. What does that mean? What I'd like you to do on the top of your page there, just above all that, I would like you to write single or upper story, long side. Just write it on the book as a cheat. Single or upper story, long side. All of the 4 pressure tables that we're looking at, 8.2 through to 8.5, have exactly the same layout. Across the top here is the pitch of the roof. So you select what the pitch is. Now, when you look at our plans, can go to your plans, please, to tell me what the pitch of the roof is. 23 degrees. Why would you choose 23 degrees? I'll give you a hint. I'll give you a hint. Huh? Aerodynamic. That's not such a silly thing to say. Can I get you to have a look at the N2 chart here? N2, a W of 10. Look at the roof pitch of 0 degrees. What is the pressure? 0.84. Now go to 5 degrees. So as the roof pitch comes up, the pressure comes down. 0.62. 10 degrees, 0.52. So it's reducing. 15 degrees, 0.48. 20 degrees, it starts to increase again. 25, it's increasing up to 0.72. So on and so forth, right up to 35 degrees, where it's 0.75 kilopascals. So what it actually did, as the roof pitch increased, the pressure dropped, but then it reached a point where it went up again. Let's explore that really quickly. Remember Dr. Bernoulli? What we had, the original building we looked at, was a flat roof. So as the wind come over, all the wind arrows, the wind compressed, went up, over like that, and down here, like so, and formed a bubble on the side there. So we've got this large volume of Bernoulli, or vacuum. This was what happened in Cyclone Tracy, but then we got a 5 degree roof pitch in here. It's 5 degrees, just believe me it is. But what we've actually done now is decreased the volume of that Bernoulli. So as the pitch comes up, you're decreasing the volume of that Bernoulli bubble, for want of a better way of wording it, till you reach 15 degrees. And again, I'm not sure if that is 15 degrees. And over 15 degrees, the reason it increases, this has decreased, is that we get a Bernoulli now starting at the apex. And we're also, if you think about this one, what you're doing is reducing the size of that one at the outside. So the further this pitch comes up, this one reduces, but another one forms at the ridge. You'll be spreading them instead of only coming one place. I'll be spreading them. Spreading the Bernoullis out, yeah. Another way to look at it from a bracing point of view, it's quite easy to look at this from a tie-down point of view where we've got uplift. But the best way to explain this is think about the guys carrying glass around on the building sites where they're using the suction caps. So if you've got the suction cap on the edge of that building that's sucking onto this roof surface, it can actually give you that resistance. Another way of explaining that is this. If I put that glass of water there, whatever wind hits this end of the building, it goes right through the ceiling diaphragm to the other end of the building. And that's what this long side and short side wind directions are about. Whatever happens here is going to happen here. You see the glass of water again with floaties in it? But it does these ones. Okay? So that's what that 2 wind directions is all about. But it's like, it acts like a suction cap. For you more elderly gentlemen in the room, do you remember years ago when we were building these houses at 17.5 degrees? Does anyone remember that? Remember there was a couple of them that we started doing, and I'm thinking to myself, why would we be building a house at 7.5 degree roof pitch? If you have a look at those numbers and that table, somewhere between 15 and 20 degrees, based on that table, is the optimum roof pitch. And that's the answer why we were building them at 17.5 degrees. No, the building code come about from 74, but when Cyclone Tracy happened and destroyed all these wrap-over roofed houses up there, just about every house in Darwin was trashed because they had a flat roof. They did more and more studies into it, and this is the reason now we have AO 1684, Light Timber Framing Code. I'll deal with W now. W is really important. W is the dimension that determines the height of the ridge. I'm building this house for Mrs. Smith. Mrs. Smith is 14 years old and she doesn't understand the ramifications of what she's about to ask me. She said, I've got this building that has a 20-degree roof pitch and this building is 8 metres wide and I want you to put a 4-metre wide games roof on the back of the building, but I want to keep the same roof pitch. She says, we can do that without going back to council, can't we? And I say, no, we can't. And she says, why? And I say, because what we're going to do is take this from what we call a complying development in New South Wales, which means it has to be of a particular height, it can't be any higher. And let's say this is 2.4. We'll make that 2.7. This here at this stage is about 1.8. She says, I want to put this games room on the back that's 4 metres wide and I want to keep the same roof pitch. I say, well, okay, we can do that, but you must understand that the roof pitch is going to be higher. So before it was 1.8, now we've just added about 1.5 onto it. So in total, the roof pitch now is what, 3.3. So W before was this dimension here, which was 8, but now W is 12. That's what my W is, because W is the dimension that determines the height of the ridge. Have a look at the diagram at the top of the page. And look where W is at the top of the page. W is parallel to the direction of the wind. Go over to table 8.3, please. Look where W is. It's in the same spot. What's different between the picture there on table 8.2 and the picture there on table 8.3? 8.2 is a single-storey building. 8.3 is a 2-storey building. Here's your cheat for table 8.3 at the top. Can you write ground floor long side? So that's the difference between the two. Because it's long side, W still remains the same. It's parallel with the direction of the wind. 8.2 is long side, 8.3 is long side. Now when we go to table 8.4, what's changed? W hasn't changed at all, but the wind direction has changed. So for short side, the W is perpendicular to the direction of the wind. So what they're saying in looking at these diagrams is that W doesn't change. Once you work out what W is, it doesn't change throughout all 4 tables. This one is single or upper storey short side. And when you go over to table 8.5 here, this is ground floor short side. W is exactly the same there. Can I ask you to write that across the top of the page, please? Now, table 8.5, turn the page, please. Ground floor short side. That's what table 8.5 actually says. It reads as this. It reads as pressure on area of elevation, lower storey or subfloor of a single storey or 2 stories, short end of building, hip ends. That's what it means. Ground floor short side. I want to do a little demonstration here on how important it is to actually make sure you're reading the correct table. I'm going to give you some information and we're going to pull it apart and have a look. And I always do this demonstration because it can make a lot of difference. It's absolutely critical that you read these tables correctly. Now what I'm talking about here in pressure, I'm going to talk to you about the difference of 0.1 of a kilopascal by reading the pressure wrong by 0.1. The information I'm going to give you is N3, a W of 10 and a roof pitch of 25 degrees. I want you to go to table 8.2 and find that, please. Huh? W is 10. W is 10. Yeah, it's 10 metres, yes. Technically it is, sorry. But a W is 10. I think it actually states that on the side of the table, doesn't it? Yeah. W in metres. So N3, N3 is here, see, over the page. A W of 10, so we're on that line there. Roof pitch of 25 degrees. And you come up with a resistance of 1.1. I hope this is going to work out. I haven't done it in N3 before. I know it works in N2. 1.1. Now go to table 8.3 and use exactly the same information. N3, a W of 10, a roof pitch of 25 degrees, and you come up with 1.3. Now, just in analysing that and looking at the diagrams at the top of the pages on those tables, what's the difference between that and that? What do you reckon the difference is? No, the wind direction is exactly the same on both of them. W is exactly the same, the roof pitch. What did you say? Yes. He technically is right. He said the height of the building. What it's about, if you think about this, what we're talking about is that's the roof pitch, so it's that distance there, whatever that one is. Single story building, that's the height. So they've got, the proportion here is this much flat surface and that much sloping surface. And on this one here on table 8.3, the proportion of flat surface actually increases. There's a lot more flat surface using the ground floor of the building. That's why the pressures are different. So it's important that you understand that. Short side, table 8.4, using the same information, go and find the pressure, please. N3, a W of 10, a roof pitch of 25 degrees, 1.2. Now let's stop there. This is long side, single story long side. This is ground floor, single story short side. Why is the pressure greater on the short side than it is on the long side? Well, it is, but if you think about what the short side looks like, there's a larger proportion of flat surface again to sloping surface. So this is what it's all about. It's the proportion of flat surface to sloping surface. And the last one, ground floor short side, table 8.5, N3, 0.61. Are you on N1, son?
No, sorry, I'm in N1.
He is in N1. That's, turn the page to N3, please. Thank you. There's N3 there. That's not uncommon. You guys are going to face that today. You've got to make sure you're red-blooded Aussie males. You've got to stop and make sure you're reading the right tables. Wait till you get into member sizing. It's a nightmare. So it was 1.3. Oh, now I'm in a spot. Why are they the same? They shouldn't be. What you'll probably find is this is 1.31, this is 1.39. I'm assuming that's what it is because you have to work out the difference between the two. What if we messed this up and it was 1.2? It's only 0.1 of a difference, isn't it? Can I tell you that the long sides, if this building is 16 metres long, the one we're assuming, that area is going to be around about 90 square metres. Seriously, that's not uncommon to have a 90 square metre area of elevation on the long side of a building. 90 square metres times 0.1 equals 9 kilonewtons. That's what it equals, a 9 kilonewtons. And you go, well, what does that mean? 9 kilonewtons is 3 sheets of ply. That's the difference between your building standing up and falling down. That is why it is absolutely critical that you read these tables correctly. And it's one of the key things we're looking at. If you can't read these tables correctly, we'll send it back to you straight away. That's the first thing. You've got to get that right. okay? And the area's got to be pretty close as well. But that is where it becomes critical, that 0.1. Once you work it out, and in this case we worked out at 6.69 for task 57. So 6.69, there's no W there for 6.69, is there? Which one are we going to use? 7. 7 is the golden number for task 57. There's no row there for 23-degree roof pitch either. Which one do we use? 25. Thank you. Common sense. So let's get on with this. Tributary area. Now again, what I want you to do with tributary area is think about beams. I'm going to explain it to you this way. Here's my bracing beam, for want of a better way of wording it. So there's 10 kilonewtons on each one of those. 5 kilonewtons comes down here, 5 kilonewtons comes down here, 6 kilonewtons comes there. Would you agree? Yeah? So at this point we've got 5 plus 6 is 11 kilonewtons. That's the beam, you agree? Now I'm going to stand this beam up. This is the roof area, this is the wall area. I'm going to apply a point there and a point there, and this from now on will be known as the ceiling diaphragm. Here's my roof load. By applying roof bracing, what I'm actually doing is transferring the load down into the ceiling diaphragm. By applying wall bracing, half the load goes that way, half the load goes that way. By applying wall bracing, what I've got to do, what I'm doing is taking the load from there down into here. That's what bracing does. So this was 6, this was 10, this is 11 here, and this is 5 here. So my area, in this case, the height of this building that is applying load up into that ceiling diaphragm is that distance there. Now, have a look at table 8.2, at the diagram at the top of table 8.2, and what you'll notice is the shadow lines on the bottom there actually come in halfway up the wall. Can you see that? And the reason is quite simply this here. We don't have to worry about this area, it's taken care of. It transfers automatically down into the floor. The top half of this wall turns up into the ceiling diaphragm. All the roof load goes into the ceiling diaphragm. We need to take that load out of the ceiling diaphragm into the foundations. It looks like this. That's that roof beam. All the roof load goes into the ceiling. The top half of the wall goes into the ceiling. Put the bracing there and we transfer that down into the ground. Now I'm going to continue on with this beam. What I'm going to do is make this a 2-story bracing beam. And just to mix it up a little bit, I'm going to put a load here of 14 because I want to, because I can. So what we've got now is we've got 7 here and we've got 7 plus 5 here, which gives us 13 kilonewtons, sorry. And that remains the same. So now when I stand this up, I want to introduce you to the floor diaphragm, which is here. This is the 14. So that's 14 there, plus 7, 13. He's did that on purpose. So that's the 2-story bracing beam. That's the area of elevation for the single story, which we've already determined looking at the diagram at the top of 8.2. If you look at the diagram at the top of 8.3, table 8.3, you'll notice that dotted lines on the area of elevation come in halfway up the ground floor. And that's the reason why. So let's look at this again. The roof load gets transferred into this upper floor ceiling diaphragm. The top half of that wall goes into the ceiling diaphragm. We take that out of there and we put it into the floor diaphragm at this point. Once we do that, we need to then take that area again out of the floor diaphragm and take it down there. Then we've got to introduce this area here, which needs to be taken out as well. So in actual fact, when you look at that diagram there, and you look at this, upstairs gets counted twice. It's like, that's the area for upstairs, and that's the area for downstairs.
Absolutely.
More bracing into downstairs than there is upstairs, absolutely. Because you're taking, all you're doing by putting bracing upstairs is getting that roof load and the top half of the wall load into the floor diaphragm. And then you've got to take that roof load and upper floor wall load out of the floor diaphragm, as well as that extra flat surface. And we know that that extra flat surface has a higher pressure on it because we looked at that back in table 8.1. So that's basically how you do it. And so if that was short side, just to review that and extend on that, long side actually looks like this. So your upstairs long side is this part. Single or upper story long side tells me 8.2. Single or upper story short side, using those cheats in my mind, tells me 8.4. Ground floor long side, when I use those cheats, tells me table 8.3. And ground floor short side tells me 8.5. So when I say that to myself, I say, what am I working out here? I'm working out single or upper story short side. So what I do is I go to my cheats in my book, single or upper story short side, table 8.4. I go to table 8.4, open it up, look at the diagram at the top of table 8.4, and it tells me that is the area I have to calculate. And then if I was, the thinking again is, if I'm doing ground floor long side, I think about my cheats, and I know that tells me to table 8.3. I go to table 8.3, I open it up, I look at the diagram at it, and it tells me that's the area I've got to work out. So that's the thinking behind it. That's why I introduce you to those cheats. What you're actually doing here, when you're working out bracing for a two-storey building, there's 4 calculations. Force equals pressure times area. The area is going to be area 8.4, pressure from table 8.4. So that's the red area. The next one is the blue area here times the pressure from table 8.5, and that's for short side. Long side is the red area multiplied by the pressure from table 8.2, blue area multiplied by the pressure from table 8.3. So they're the 4 calculations that you've got to do. So that's the area of elevation for a two-storey building. I'm going to do an example with this. We're going to do short side upstairs, and I'll show you how to actually apply this to your assignment. Here it is here. Here's an example here. Now, this example is kind of a fair way out in that I don't believe this 20 square metres, but it's an example of how it actually works. Okay, now we've determined the area of elevation, which was step 4. Now we've got to determine the bracing. At each level, for each elevation, there's 4 calculations. There's 2 levels and there's 2 elevations. Short side, long side, upper story, ground floor. What you would actually do here, you just put it in. Put your bracing in like you normally would. Add up the value of the bracing you've put in there and either subtract it or add it to get it more accurate. That's basically how you do it. Okay? And there's a couple of rules to this that we need to sort out. Go to page 142, clause 8363. I want you to look at the last paragraph. So the numbers that they actually give you in here, the values they give you in here of the sheet bracing is worked out on J4 and JD4. Can you remember what J4 was before in joint groups? It was American Oregon, but we don't use anymore. Brace types. Now, there's 4 basic types of bracing. They're all in here in table 8.18. Now, I just want to bring something to your attention here, is the heading at the top of it. It talks about the maximum wall height being 2.7 metres. Okay? Anything over that, at the back of the table there is a height multiplier. You go in and use that height multiplier. So the four types are basically metal strap, metal angle, sheet material. The metal strap is tensioned. I like metal strap internally. You should always try and use metal strapping internally. Metal strapping I like quite well because all you've got to do with metal strapping is go up, put the metal strapping on the wall, nail it to the top plate, nail it to the intermediate studs, that's it, full stop, end of story. By doing that without stud straps, for every metre I can get 1.5. So if I've got a wall 2 metres long with that flat metal strapping on it, I get a resistance of 3 kilonewtons out of that. There. What they're talking about, the resistance that's given here is kilonewtons per metre. And what they're talking about is the width of the panel across here. And the minimum width is 1.8 metres. Because the wall's 2.7 high, anything less than 1.8 metres turns that bracing system back into tall and skinny, which will rotate really easy. So we've got to keep this, again, for want of a better word, we've got to keep this short and fat thing happening. So the minimum width is 1.8 metres and the maximum is 2.7. We are very keen for you to show us this in your task, okay? If you need to have metal strap bracing any wider than 2.7, understanding the minimums, what you'd have is 2 at 1.8. Not 1 at 3 metres or 1 at 3.6, you'd have 2 at 1.8. So you need to demonstrate to us that. The other thing is, the other parameter is the angle. Must be between 30 and 60 degrees. Okay? The same applies, that information that I've just given you, those parameters, apply for all your metal angle and metal strap bracing. So that's what we call a type B system. The other one there, the one there with 3 kilonewtons per metre is this one here, which is a type D system if you go over the page. And it's basically exactly the same, it's basically similar to type B, however you have stud straps at the top and bottom. So you've got stud straps at the 4 points. And that one there is a very effective system. Will give you 3 kilonewtons per metre. So if we had a wall that was 2 metres long, you get 6 kilonewtons of resistance out of that system. Now, here's something I don't get. Angle bracing. If you think about the work that goes into putting an angle brace in, the maximum depth of a cut into a stud is 20 millimetres. Okay, that's it, full stop. So you've got to set the saw at 20 mil, run the saw across it, put your angle bracing in it, and then nail your angle bracing off. So there's a bit of work in what I just told you. If you look at the type A system back on page 143, for doing all that work, you're going to get 0.8 of a kilonewton of resistance. To me, there is absolutely no value in that. That seems like a lot of work. And it's not one brace, it's 2. It says 2 diagonally opposed braces. Doesn't make sense to me. The other one is the type C bracing over the page on page 144. You've still got to cut the angle in, but what you've got is 3 stud straps. 1 at the top, 2 at the bottom, and you're forming a triangle. Okay, if you think about the same principle as a truss, the forces will just keep going round and round and round in that shape. But again, for the work that you're putting in there, what are you getting out of it? 1.5 kilonewtons per metre of resistance. Now, I'd argue that putting 2 metal straps on there, nailing it to the top plate, nailing at the intermediate studs is a hell of a lot easier than doing that. The other thing against angle bracing, if you think about it, if I've got a 90 mil beam, aka a stud, that's all a stud is. A stud is a vertical beam, okay? But let's pretend it's a beam this way. Then I put a 20 mil cut in it. How deep is that beam now? Exactly. You're reducing the carrying capacity of that stud. So that's the thing I don't get. I'm not saying don't use it, but just consider what we just discussed. Sheet material. Basically, the 2 types that we've got mentioned in here are hardboard and ply. There's this OSB board that's about now. The OSB board, the best way to explain it to you, you've seen your I-beams, the webbing in the I-beams with the particle board in there with the big chips in it. That's OSB board. Good stuff. Okay. I'm not going to talk too much about this one here which is the boards, at a 45-degree angle, because the last time we did that was when? 1970? Or are you guys still doing that? Come on, you're not 30 years behind New South Wales, are you? Very good. The only thing I want to talk about here, and I want to introduce you to that again, is the distance of the nail centres here. If your nail centres are 60 millimetres apart, those boards at a 45-degree angle will give you 2.1 kilonewtons per metre of resistance. But if you pull your nail centres together closer, at 40 millimetres apart, you'll get a resistance of 3 kilonewtons per metre. So again, this gets back to the fact, what we discussed this morning about joint groups, and it gets back to the fact of pulling the nail centres closer together will give us more resistance. There's another one here in the middle, and this is one I really want you to take notice of. When you're using bracing, or when you're determining bracing for a building, and you get in a spot where it's a 50-50 call, whether you can actually get the numbers or not, I want you to use type F. And type F is basically phone a friend, call an engineer up. Don't put yourself in a tricky situation, okay? You will, honestly, you will come up with these plans that are stating this. Tie down bracing and member sizing in accordance with AS 1684. Now, by the end of the day, you're going to be able to work this out. But if you come to a situation where you've got full glass wall here, full glass wall there, that's a bracing wall and that's a bracing wall, how are you going to get the bracing in that end wall? And the answer is type F. And it'll basically be a steel beam and a column in the corner. Type G, let's get there. Now, this is quite interesting when you have a look at this. They talk about two stud spacings over here on the right-hand side, 450 and 600. And where you've got a wall with no noggins in it, I think that's a bit funny. We won't even discuss it. We'll talk about the ones down here with one row of noggins in it. And what you'll notice, without the noggins in it, you'll see that you need thicker plywood to span the distance between the studs. The further apart, at 600 you need a 9mm, at 450 you need a 7mm. But when we've got the noggin in the centre, which is doing that job, the thickness of the ply doesn't change. The only thing that does change with regards to thickness is the stress grade. Now the little warning there is don't buy your ply bracing from Mr. Ply and Wood. That is not structural plywood. It must have a stress grading. So you ring up your timber yard and you say, what stress grade of bracing ply do you have in stock? If he says F27, you go, beauty, I'm doing a type G. Send me out a pack of 3mm, please, or whatever. How many sheets you need. That's how you deal with it, basically that way. Nail centres for type G are 150mm on the top and bottom plates, 300mm for your intermediates, and 150mm on your vertical joins. Okay? They're your nail centres, and that's the value that it give you, 3 kilonewtons per metre. That's the standard system that you are using now in a veneer wall, where you're putting it on the outside of the wall. And just going back one more step too, you can put ply bracing on your internal wall, I'm just talking practically now, providing you sheet the whole wall, so you don't have any steps in it. And that is quite common out there in the field now. Now a couple of things. Remember what I said about reading some notes? Down the bottom, note 1, for plywood fixed to both sides of the wall, see clause 8365. So what they're saying is, if you put 3 kilonewtons per metre on this side of the wall and 3 kilonewtons per metre on that side of the wall, the total value of that system is 6 kilonewtons per metre. So you can double it up. It then goes on to say, nailing shall not split the framing. Duh. So that's the restriction against using that 6 kilonewton system, because when you get to that 6 kilonewton system, they're talking about putting nails at 50mm centres. And if you've got a 70mm wall frame, nails at 50mm centres, there's a fair chance, if it's crappy pine or something like that, that you're actually going to split it. So that's where it's sort of, you need to be a little bit careful with it. And then it goes on to say, and the connections at the top and the bottom of the walls shall be increased to match the combined capacity of the bracing plywood system on each side. So when we're going to change it from 6 kilonewtons per metre, it would have said that we need an M10 fixing at the end of it, for argument's sake. But when we change it to 12, we might need to have M16s or M20s or something like that at the end of the panel. So you're allowed to increase the value of the bracing, but you have to increase the capacity of the fixing at the end. That's what those two clauses say. Now, unfortunately, us blokes with the new standard, that clause has accidentally been left out. It is you can do it. Okay, they haven't taken it out for a reason. It's actually a mistake. So you can double side your bracing systems. Hang on a sec, let's deal with it now. It's called nominal bracing. And what nominal bracing is your internal lining boards. Now, earlier we discussed safe working loads, and this is the thing why I want you to be efficient with your bracing. If you go back and think what we've done, when we did our wing classification, we bumped it up to the next level, didn't we? So already we've got some safe working load in there. Secondly, with your nominal bracing, it can equal up to 50% of the total value. So it can use half the value of it. But what we say to you is work out your bracing accurately, very, very accurately, and use this nominal bracing on this page as your safe working load. A couple of things here. Bracing capacity is given in table 8.18 for plywood. The minimum length of the panel shall be 900 millimetres, which is what it says here, except type H, method A, can be as low as 600 millimetres wide. So can I ask you to do what I've done in my book? If you need a short wall system, which you do, method A there, just put an arrow above it and write minimum 600 like I've got in the book here. But it's only method A. Type H, method A. So you've got a sheet system which is type G, or all sheet systems are a minimum of 900 wide, except for this one, H, method A, which is 600. If you need a short wall system, go to type N at the back, N for Nelly, the hardboard system at the back. And what you'll note at the bottom there is you can use that system down to 460 millimetres. Okay, that's your short wall system. So all your sheet systems are 900 wide, except H method A, which is 600 wide, and type N is 460 wide. Now, I point that out to you because the plan that we have in this book is really, really simple. And if you could build houses like this plan all your life, you'd have no problems. But that ain't going to happen. You're going to have so many situations where you need to use these short wall systems. It's just the way the designs are these days. So that's that. Let's go and have a look at type H, method A for a start. I'll draw a wall that's 3.6 long so I can describe this to you a lot better. What all that gobbledygook says is that for method A, your nail centres at the top and bottom can be 150 apart. Your vertical sides are 150. Your intermediates are 300. That's what it's telling me. But it goes on to say, for method A, M12 rods shall be used at each end of the sheath section, top and bottom, top plate to bottom plate floor frame. Method B has no sheathed rods, but shall be nailed to the top and bottom plates at horizontal joints of 50mm centres. Now, what that means is, with method A, you've got a rod at the end of the panel and a rod at the end of the panel. And your nail centres are 150 horizontally and 150 vertically. That's method A. Down the bottom left, right-hand corner here, down in here, it states method A, M12 rods as shown, plus a 13 kilonewton capacity connection at 1200mm centres. So you have that rod there, but you need to put an anchor in at 1200 centres, read Chemset or whatever, like that across the bottom of it. So that's method A. Method B, delete the rods. You've still got to have these connections across the bottom at 1200 centres, but your nail centres now go to 50mm. So that's a hell of a lot of nails. And this is what I was saying before. What's that value there? That's 5.25. If we double side it, that's 10.5 kilonewtons per metre, 3 metres long, 15 kilonewtons plus. Very high capacity system. but you've got to be very careful you don't split the wall frame. Split the wall frame, quite obviously, it's a wasted exercise. So that's that one there. I, at the bottom of the page, is basically the same as method A. So you've got these rods in here. You've got your nails at 50 mil here, but they're 100 mil on your vertical edges. So they're 100 mil up here. Now, instead of being 150. And now what you've got is tie downs here at 600 centres. So you've got to have 13 kilonewton connections right across the bottom at 600 centres. So you're starting to talk about a really, really high resistance system. Now you've got that, a maximum there of 7.6, double-sided, 14, 15.2 kilonewtons per metre. A 3 metre panel, 45 kilonewtons. Now you guys in Brisbane aren't likely to need that. Old mate in Cairns, working under C3, will definitely need it. He will have to use that system up there. Now this is a national licensing system that you're entering, so you need to understand all these bracing systems. If you go to build a house in Darwin or Cairns, that's the system you're going to be looking at. Even in N4, you may have not a lot of walls to deal with in non-cyclonic, but you will need to use a double-sided system like that. Distribution. Now, can I get you to go to clause 8366, please? The most important sentences from a bracing point of view, and this is about distribution. Bracing shall be approximately evenly distributed. Now, what that means is approximately even values at approximately even distances. Now, by way of explanation, I'll do this quick little diagram for you. Now, let's say I sat down and I calculated 30 kilonewtons of resistance. I've got to find 30 kilonewtons. So what I've got is this building that's really ugly, looks like this. Something like that. What that actually means is, this is the way I do it. What walls are available to me to put bracing in? The answer is 1, 2, 3, 4, 5, 6, 7. Because there's this thing called the ceiling diaphragm. Everything has to be connected into the ceiling diaphragm. And we'll explain that in a minute. But whatever happens from this way, where's my cup of water? If I've got pressure hitting this end of the building, I can put the bracing here or here to give me that resistance. Would you agree? Doesn't matter where it is in there, because it's all connected in through the ceiling diaphragm. Same from this direction. Whether I put it on this side over close to this side or over close to the other side, it really doesn't matter. What does matter is the practicalities of this. If I don't have any bracing on this back wall here, how am I going to straighten this wall before I put my trusses on the top? I really can't, can I? Unless I have some form of temporary bracing. I really can't do it. So what I need to do is say, righto, I'm going to put some bracing over there, so I'm going to use that one. I want to put bracing here and here probably, and I probably want to put some bracing there as well. So they're the ones I'm going to use from a practical point of view. But you may want to do this. If you look at that and wipe that out, that's approximately 1, 2, 3, 4 spacings that are roughly equal distances apart. You wouldn't have in this building all the bracing over in that wall, would you? Because otherwise you apply pressure here, this side collapses, causes this side to fall in on top of it. So that means now that I've got 1, 2, 3, 4, 5 walls to deal with. And I'll actually just put this here like this. So I'm going to have one there, one there, one there, one up that wall and one up that wall. I said I had 30 kilonewtons to distribute. 5 divided by 30 equals 6. So I've got to get approximately 6 kilonewtons in each one of those walls. It's as simple as it is. 6 kilonewtons. Okay? And if you remember type G plywood, has a resistance of 3 kilonewtons per metre. I'll put 1 metre there, even though my sheet's 1.2, but in heaven all the sheets are 1 metre. 1 metre there, 1 metre there. 3 kilonewtons, 1 times 3 equals 3. 3 plus 3 is 6. My type D strap bracing has a resistance of 3 kilonewtons per metre. I'm going to put 2 metres in there, which equals 6, 2 metres there, which equals 6, and 2 metres there, which equals 6. That's basically how you're going to do it. So that's what that clause says in those two sentences. Bracing shall be approximately evenly distributed. That's what the first sentence says. The second sentence says bracing shall be initially placed as close to the corners as possible. So I've got 1 there on that corner, 1 there on that corner, 1 on that corner, 1 on that corner. Okay, that's basically how you go through it. It wouldn't be any point, I could put it all in those end walls, couldn't I? And what had happened to the middle? The middle would just go, which would pull the ends in. You need to do all your bracing, fix it all off and finish it all off before anybody goes up on the roof. Because sending someone up on a series of frames that aren't braced off correctly, well, I don't have to tell you the outcome of that. So, this structural ceiling diaphragm, this is the thing, and that's what this was all about. All this bracing has to be connected to the external wall, because otherwise, if we did it here like this, if you thought about this as a beam, the centre of this wall could actually bend, and that's what happens there. It goes into the ceiling diaphragm, as the structural ceiling diaphragm, which distributes that bracing around the building. Resistance must be parallel to the direction of the wind. So here's the wind on the long side of this building, assuming it is the long side, and that's where the bracing is. The bracing's been put in parallel to the direction of the wind. Here's the wind on the short side, and the bracing's been put in there, again, parallel to the direction of the wind. Spacing. Now, this distance apart here is important too. Remember we spoke about studs before? If I didn't have that noggin in the centre of the stud, when we had this load compressed on the ends of that stud, it can actually deflect and buckle in the centre of it. And that's the reason behind the noggin. So it's exactly as we say here. If I haven't got this bracing in here at these points, when we apply a load, again on the centre, you end up with these ones happening. Now, for your N1 and N2 wind classifications, generally it is measured at 9 metres. Down the bottom here, it says, for single or upper story of two-story construction, the maximum distance between the brace walls at right angle to the building's length or width shall not exceed 9 metres. Now, there's some PCAs running around, certifiers, who don't understand this. They think that means when I'm looking at this wall, I've got to have a brace in there at centres not exceeding 9 metres. And that is incorrect. What they should be saying is you've got sheet bracing in the outside walls here, there and there, for wind B, short side. The distance is 10 metres. They should be saying to you, well, you've got to put something on the inside walls. And I mean, again, I'm sorry, common sense, but you have to do it. Okay? Now, if the wind is higher pressure hitting that building, you then need to go on and pull those centre closer together. Now, how the hell do you work that out? What it goes on to say, it says, for wind classifications greater than N2, the spacing shall be in accordance with table 8.20 and 8.21. Now, in our case, N3 we're dealing with, aren't we? We need to know what our ceiling depth is. Our ceiling depth, again, is this distance down the side. See the diaphragm depth on the side? So we'd be looking at this table here is for wind classification N3, roof pitch of 25 degrees, a W of 7, the maximum width of our maximum spacing is 7.1 metres. So technically on the short side of our roof, we only need to put it in the outside walls. Please don't do that. Okay, that's what they're saying here, technically, but we'd rather see you put something in the centre, obviously. Bracing both sides of the wall we talked about. Fixing capacities, when you do that, the fixing capacities at the ends will have to be combined. Connection at the top of the bracing units and connections at the bottom of the bracing unit. if you can have a look at this, what we're doing here, here's the wind hitting this building on the long side. In order for me to resist that wind, if I've got no bracing in there, that ceiling diaphragm will actually bend. So what we do is we install this bracing. This is the bracing in the centre. Well, what you'll notice is this one here is independent of the external walls, isn't it? And there it is there. So unless it needs to be connected at that point, right there. How do we do that? We use this system. In a truss roof, trusses are made with camber, okay, so that when we load the roof sits down level. Now, as the truss is made with camber, it needs to have a gap between the internal wall frame and the bottom chord of the truss. So this block and this block here, they are nailed onto the top plate only to give it this sideways resistance, but it still allows it to come down. I'm just going to deal with that really quickly because you don't have to worry about that for task 57. That one there is where the trusses cross the wall frame at 90 degrees. This one here is where the trusses are parallel. So you just nail a trimmer in between. That can be done with nails, bolts, type 17 screws, whatever. It's all there in the book. When you've got nothing better to do, have a read. Connection at the bottom of the wall. All I'm going to say about this is just quickly, for a 2.4 metre high wall, remember we spoke earlier about a type G system that I was going to double side it? That meant it increased the capacity up to 6 kilonewtons per metre. So you look there, the wall was 2.4 high. I've got to put a 14 kilonewton capacity connector at the end of that brace unit. I've got to have 14 kilonewtons there to stop that brace panel from rotating. What are the connections that are available to me? If it's a timber frame, they're all there. They're all there on that page there. When you go over the page, here's the ones for the slab. And basically you've got two types, cast-in bolt, which old mate's doing up in Cairns, or chem sets. As we discovered this morning, that's about it. That's all you can use. And for chem sets, refer to the manufacturer's installation instructions. What I actually suggest you do if you're going to continue doing this is form a business relationship with a fastening company. If you ring up Ramset, he will be there quicker than Flash Gordon, believe me. You ring him up and say, I need some 14 kilonewton connections for a slab, he will be there as quick as you like. All these guys out there at the moment, it is a really, really cutthroat competitive industry for fasteners. There's Hilti, there's Bremick, there's Powers Fasteners, there's Ramset, there's heaps of them. So just ring those guys up. You don't have to take that responsibility on yourself. You don't even have to look on the net. Ring them up and say, I need some 14 kilonewton connectors. Don't bring Dynabolts. For obvious reasons. Or screw bolts. Yeah. So that's that. M12 relates to the shaft size of the bolt, not the hole size. Okay, be very careful with that. The edge distance, yeah, we discussed all this morning. Well, there's a screw bolt there. We've already discussed that. Now, we're getting close to the end here where we can start working on an example. I said to you earlier, this will only ever be a problem when the building blows away. This building here, this one isn't at Cape York. This is in Region A, in a paddock near Bathurst, New South Wales. The terrain categories are very high risk because there's no trees around it. It's up on a crest, so remember we spoke about topography this morning, so on and so forth. It only ever becomes a problem when the building blows away, whooshka. There it is. Now let me tell you the story behind this. It goes like this. The building, the floor plan you need to know. The floor plan is something like that. 3-car garage on the end, one garage, one roller door, 2 roller doors, 3 roller doors, 350 brick piers. That's it. Now you think about what you know about bracing now. I've got resistance back here, resistance here. Yeah? Resistance here, resistance in the centre of the building as well, resistance here, resistance in the centre of the building as well. What have I got on this end here? Now, a builder has a duty of care, now that you know about this stuff, before you come in today, you had the ability to plead ignorance. I don't know, I've never been shown this. Well, now you have. You have a duty of care to recognise the potential for a problem here. And remember what I said about type F? Phone a friend when you see this. There's something he could have done here, and it's what we call diaphragm bracing. All this wall here is a super bracing wall. What we basically do is take more bracing and put it up in the ceiling diaphragm. So if you picture this one, here's this bracing wall, and if it's done correctly, you get this sort of resistance in it. But you need to recognise the potential for that problem there. This guy didn't. That there is a truncated girder truss. And we all know truncated girders, major structural component, primary structural element. Here's a better view of it. This is from this end of the building. This swing set, that swing set, they reckon is what actually started this chain reaction here. That swing set comes from the neighbouring property, 2.5 kilometres away. It apparently punched a 50mm hole through this roller door that used to be in this opening, which pressurised the garage, which blew the top off and blew that roller door back around here in through this window. That's that window there. That window happens to be the main bedroom. This one here is very difficult, but brickwork has fantastic bracing capacity. When a brick wall is up to 10 metres long, it has a resistance of 6.6 kilonewtons per metre. So the longer the brick wall gets, that short and fat thing happening, the more resistance it has. It's quite good. But from a sideways point of view, it has nothing. And that is one of the big problems with brickwork. Brickwork needs to have these side braces in it. And that's what happened here. Once this roof went, the walls collapsed in, and we had all sorts of problems going on. Now, the last thing I want to tell you, this was designed for wind classification N2. If they would have taken this fight on a bit further, which they didn't, they reckon they could have argued that it should have been determined as N3. So when you build something to N2, that means 144 kilometres an hour. N3 is 187 kilometres an hour. That car there was parked there in front of that ute. That car actually blew around to that point. So that's the type of thing that can happen. This is why you have insurance. The homeowner made a claim against his home insurance. When the engineers got involved in it, they come out and they said, no, it's a problem because the builder didn't recognise the fact that he had this bracing issue here, plus there was a tie-down problem. They didn't have any straps in the piers to tie that perimeter beam over the top of the piers. Now I need to tell you who the builder was, the homeowner. So not only is he in trouble for not being there, he's in trouble because his house blew over. And now the insurance company says, well, you've made a claim against us, but the building's been built poorly and you're the builder. So they basically said to him, see you later, mate, we're going. Walked out. $97,000 worth of repairs that he had to stump up for. So this is what you guys have got to do. You've got to recognise the potential for a problem, and that's what you've got to build against. Member sizing is actually, I'll just talk to you quickly about member sizing. We've got to introduce you to two new things. One of them is called floor load width, and one of them is called roof load width. Basically, you go into the index at the front of the book, and the index actually tells you for floor framing what clause it is. So you go and find that clause in the book, and to give you an example, clause 4.3, I went through the index and it told me to go for floor framing, go to clause 4.3. And when I read clause 4.3, it says, the size of bearers supporting single or upper story load-bearing walls shall be determined from span tables 1 to 4 for floor load widths of 1200, 2, 4, 3, 6 and 4, 8. So that's for single or upper story. Then it goes on to say the size of bearers supporting the lower story of two-story load-bearing walls shall be determined from span tables 33 and 34. So that's how you do member sizing. Once you understand floor load width and roof load width, which you have to work out yourself, you actually go to that CD, to those series of tables. And the important thing is table 1 to 32 is for single or upper story, 33 to 48 is for your ground floor. And the layout of what I just read out to you is always the same. The format's always the same. The first floor is always in the first paragraph, Second floor is always in the second paragraph. Okay, task 57. I'm going to show you how we actually put that information I've just given you in the last couple of hours into practice. The first thing I've got to do is calculate the area of elevation. Now, the one we're going to do here is single story short side. Looking at the diagram, that this here is the area of elevation I have to calculate. 8.4, and that's the area of elevation. Now this may help you as well. You shouldn't lose this. I'm going to tell you that the ridge height is 1.44 metres. You'll have to believe me on that. Where did I get that from? That sketch? I went to the elevations. There it is there. It's right there. That's the sketch. Okay? While I'm on that same subject, where did I get the sketch from for the long side? Again, from the elevations. Now, I'd just like to point out here, that's a balcony where the wind can just blow straight through that balcony. There is no resistance. Okay? Same with that one at the back. There is no resistance. But there is resistance on the roof area. So that roof area needs to be calculated. So does that wall section in there, but not that section there. The wind just blows straight through there. Okay, so that's what the shape actually looks like. So, how I'd do this is this. I'd go area A plus area B is how it works out. And what's the formula for area of a triangle? Correct? And I can tell you that that comes to A equals 2.52 m squared. You'll have to believe me on that. How would I find out how high that wall is? It's on the elevations of the plan, and the elevation says 2 metres 450. So it's half of 2 metres 450, multiplied that by that 6.69, and it comes out to be 8.19 m squared. So the total area is 10.71 m squared. So that's the area. So the calc looks something like this. Force equals pressure times area. Force equals pressure. We already know it's got to come from table 8.4. Now, we've already dealt with this before. The roof pitch is going to be 25 degrees. The wind classification is N3. The W equals 7. So it's 1.2 little k, capital P, little a, times 10.71. This is going to be a snack, this one. .85 kilonewtons. Little k, capital N. Now, in your book, you have a thing called a bracing table. It looks like this. We can now proceed to the first step of the bracing table. What you've got on the bracing table, what we've actually just done is the short side upstairs, okay? The short side. Can I ask you to make wind direction A the long side, wind direction B the short side? So what you do, we're in this little row here, what you'll write is it'll have wind B. You'll write the wind classification as N3 from table 8.4. The wind pressure was 1.2. The area of elevation was 10.71 12.71 and the total force is 12.85. So that's how you fill out that row B there. This next step, distributing the bracing, is very subjective. In other words, I don't care how you guys actually work it out. It is quite subjective. You could use anything from types A, B and C. Now if you have a look at that plan, what you'll notice is that all the upstairs area is all sheeted with weatherboards, okay? So if I put any sheet bracing on the outside of this building, I've got to do one of three things. A, I've got to rebate that sheet bracing in, which we've already determined is not practical. B, I've got to sheet the whole wall. Or C, I've got to pack in between where we put that bracing. So in this case, where we haven't got to come up with really big numbers, what I'd actually advise you to do is to use type A, B or C. And because I like